Oh yeah, for those of you who are using Eventbrite, we're now using Eventbrite. Are we on? Yeah, I'm ready. Go, go, go. So just to let you know that you don't actually have to get a ticket on Eventbrite. It's just nice for you to let us know that you're coming, but the tickets are free and they'll remain free as long as we have space available, which looks like it's going to continue for a long time to come. So if you're not on our email list, and up to email calendar, you can use the Eventbrite link to do that. That comes around in each of our emails as well. So are we going, Gabriel? Yeah, okay. All right, so welcome along, ladies and gentlemen, to your weekly seminar series. By Laura Wright, who's come across streams where she was a scientist. She did a BA in chemistry at Colgate University. Go Colgate. And then she did a PhD at UC Boulder. So Buffs. Chemistry, the subject, infrared studies of sulfuric acid, the impact on polar and global. She did a postdoc at Gore, just almost across the road from Boulder, UC Boulder, and then moved across to the Bay Area to work at SRI International before she was hired on in the branch. She is an atmospheric chemist, as we've mentioned, and her published publications range across a large number of different atmospheric topics, uptake of formaldehyde and interactions with sulfuric acid experiments, of polar earth science.
To my mouth. Happy. Excited about my device or we've been taking a bunch of different things. We've got really good relationships with the pilots and the company that offers that aircraft, and so we can do a variety of different things over a long period of time. And so I want to give you a little bit of each, well, not each, but many of our projects today. Our payload consists of an ozone sensor, a greenhouse gas sensor, and a 10 hertz 3D wind measurement that also gives us temperature and pressure with really good resolution. So we're studying air quality issues. We're looking at data to help calibrate satellites. And we're even interested in the trans-Pacific transport of pollution coming to the west coast of the US. Each flight lasts about 2 hours, and it's a pretty different model than other NASA aircraft missions that you may have heard of, and certainly no SOFIA. But I want to start by getting everybody on the same page. So let's see. I swear, no laughing. I mean these all in all sincerity. Nobody uses the same units, and I want to start by just talking about this planet. Planet Earth. All right, distances. You'll hear me use a lot of different distance units, and I apologize for that. It's part of this weird trained as a scientist talking to a pilot thing, and so distances will be in miles. They'll also be in kilometers. I trust most of you can manage that one. But I had to look up a nautical mile. I mean, I knew it was close, and it's close, and generally I just kind of round that. So you may see some nautical miles in my slides, and I apologize. Just essentially they're miles. And you guys can handle the kilometers conversion, I'm sure of that. All right, here's where it starts getting dicey. I told my title, actually, the one that Adrian publicized, it was really flashy. I had said 500 kilometers per hour because it sounded great. It was rounded. Our general cruising speed of 250 knots is about 463 kilometers per hour. And that doesn't necessarily mean a lot. So if you want to think of it as 420 feet per second that the aircraft would be traveling, that may give you a different perspective on distance. I'm still not good with knots, but you're going to see them, so I apologize. If you want to, take out a calculator and a piece of paper, have some cheat sheets, that would be fine by me. Our transits actually are faster. Getting from here to there is sometimes boring. So our pilots will do that for us at more like 800 kilometers per hour, so about 425, 450 knots up at higher altitudes. All right, that's bad enough, but that's easy, right? That's just converting. Here's one that you may not have thought about. Altitudes can be measured in meters, kilometers, feet, kilofeet. Whack off 3 zeros and call it a kilofoot. It works just great. Pilots also talk in flight levels, which is whack off 2 zeros and call it a flight level. I think I got all of those out of the talk. But the weirdest part is atmospheric scientists talk in pressure as an altitude. So you've probably figured this out. There's the most pressure, atmospheric pressure, down here at the surface of the Earth. And as you go up higher, if you climb a mountain or go up in an aircraft, there's less pressure. So it's big numbers are at the bottom and small numbers are at the top. But we still use it as a vertical altitude coordinate. You'll mostly see it in hectopascals on the pages where I remembered to be SI. The pages where I forgot to convert to standard units, you'll see it in millibars, which is what weather folks talk in. They are exactly equivalent. We live at, if you'll let me round, we live at 1,000 hectopascals here at sea level. So as you go up from 1,000 hectopascals or 1,000 millibars, you're just leaving behind the mass of the atmosphere below you, and it goes exponentially with gravity, basically. So it's linear with mass, not with height. So when you see my axes change strangely, and I tell you it's the same data, and you're looking at me like I'm crazy, it means I've probably changed from an altitude axis to a pressure axis and forgotten to mention it. All right. Then in case you're not a chemist, let me give you a clue to the shorthand you'll see to my chemical symbols. So ozone, you've probably heard about. It's 3 oxygen atoms stuck together. It's noted O3. You've probably come across that the way that you've seen H2O for water. CO2 is now used interchangeably with the English carbon dioxide, so you guys probably know that one. And in case you haven't seen methane in a formula, it's CH4. So in the places where I couldn't fit the whole word, I crammed in the chemical symbol, and now you've got your translation. You've probably also come across mixing ratios, but in case you haven't, you'll see some parts per million and an occasional part per billion. That's really just 1 in a million, 1 in a billion, 1 in 100, we call that a percent. So you're familiar with mixing ratios, and you're going to see those on my slides as well. Since we're talking about the Earth, I'm going to just make the bold presumption that many of you live here, and only some of you study this planet. And you may or may not know the regions I'm going to refer to, like the boundary layer, the troposphere, and the stratosphere. So let me give you a little picture. Down here at the bottom, where we live, uh-oh, I just kicked out my power cord. Hang on. All right. Down here at the bottom, where we live, in the troposphere, you can see the temperatures are something like 15 C. So here's a temperature axis for you. And as you go up in the atmosphere in either miles on the right or kilometers on the left axis, you can see it gets colder as you go up. And that's our experience, right? You climb a mountain, you go up in an airplane, it's colder outside. Well, at some point, that actually stops. And we call that place in the atmosphere the tropopause. Above the tropopause, it actually gets warmer in temperature as you go up. And there are lots of reasons for that. One of them is actually the natural formation of ozone in the upper atmosphere, well, middle atmosphere. So ozone actually is formed up here in the lower stratosphere. And so this place where the temperature profile changes as a function of altitude is called the tropopause. About something like 75 to 80% of the mass, 90 in some places, is below the tropopause. It's everything we interact with. It's where most of our commercial airliners fly. It's where our weather is. Just about everything you think of when you think of the atmosphere, unless you're an astronomer, is in the troposphere. If you're an astronomer or if you're familiar with Sophia, you know you guys want to get away from all that water vapor, so you're trying to get up above the tropopause when you're trying to observe, especially in the infrared. So the tropopause is the top of the stratosphere, the top of the troposphere and the bottom of the stratosphere. Way down at the very bottom of the troposphere, down here in this rough part of the atmosphere where there are buildings and canyons and mountains, is a mixed layer, the planetary boundary layer, that bit of the atmosphere where everything is really well mixed by winds and by heating of the surface that leads to turbulence. That layer can be, say, 500 feet thin, really, in a still nighttime situation, maybe in a valley. But in the heat of the summer, out in the desert, that sucker can be 7,500 feet thick, and I'm trying to change units on you. It can be, 1.5 kilometers thick in a hot, turbulent, sunny place. So that mixed layer changes throughout the day. It changes place to place. It changes with the season. And it's mostly just an indication of if you sample anywhere in that mixed layer, you're going to get the same answer because the winds and the turbulence and the convection have mixed up all of your sources and your sinks, and they'll give you a uniform answer. So you'll see me refer to that as well. All right. Is that enough preamble? Can we get to the good stuff? All right. Here's the stuff I want to talk to you about today. You will probably notice San Francisco Bay here on the map with a red pushpin at NASA Ames. The pushpin's big enough it also encompasses SETI, where we are today. All of these different colors are different types of flight tracks that our project has sampled. I'll give you the obvious one first, way over here to Nevada. This bright, shiny place on the map is called Railroad Valley, and it's actually a bright, shiny place that satellites have used for ages as a radiometric calibration. It's physically flat, it's spectrally flat, it's shiny in most of the wavelengths that most satellites need to be calibrated at. So it's been used for ages, and a satellite that we've been investigating or supporting is the GoSat satellite, which is launched by the Japanese. And so we have quite a number of flights that take this green flight track out to Railroad Valley, and I'll show you some of that data. Here's the state border, and here's Reno for those of you who are looking to calibrate yourselves. The purple one is one of my favorite flight tracks. It starts at Ames. It goes inland to the San Joaquin Valley, to Merced, for those of you who might know where Merced, and there's an airport there that used to be the Castle Air Base. We take a vertical profile there at Merced, come offshore to a place that pilots affectionately refer to as Rains, take another vertical profile there, and come home. That gives us a pair of, let's just call them mostly dirty and mostly clean, air samples, and we'll show you some of that data as well. The red one is up to Sacramento. That's a new one for us, and I'll talk about a couple of flights there. The white one, if you haven't already read ahead, was a flight we did to go sample the rim fire in Yosemite. And this is the part where I admit that I'm going to hell because wildfire is a horrible thing, but it's a fantastic thing to sample if you're an atmospheric chemist. So while we were glad that it was no worse than it was, we were also very glad that that fire was close enough to home that we could take our sensors out to sample it a couple of times and to watch how the chemistry of a wildfire plume evolves with time. So I'm going to show you that data. Don't hate me. And then this yellow track is representative of a few different ones that we've done in the sort of middle and northern San Joaquin Valley to take a look at a variety of different sources like livestock and local ozone photochemical production. So that's a map to get you oriented, and it's also sort of my outline of how we're going to go through things. Here's where I look at your faces to decide if I need to talk about greenhouse gases, or if you all are so familiar with infrared absorption by greenhouse gases that I can just cruise right through. And I'm seeing a mix of nods and squints. So really quickly, I'll just point out that CO2, along with several other gases, are really good infrared absorbers. So they trap infrared radiation, which could be called thermal or heat, depending on your field of study. Trap infrared radiation that's being emitted by the planet and trap it into the atmosphere so it's not lost to space, and it increases our total energy budget. Substantial increases in the abundance of CO2 will actually increase the retention of heat and increase the heat budget. And global networks of ground-based measurements have seen an increase in CO2. Anyone who was here a month or so ago for Wayla's talk saw his plots there. You've all seen these plots, right? They have an annual cycle and they climb sort of from past to future. Pardon me. Greenhouse gases are long-lived. That's what makes them so important in our radiative budget. And since they're long-lived, they get mixed over the whole planet. Since they're mixed over the whole globe, satellites are a great way to study them because a satellite can observe not just here over California or not just over the US where the paperwork is easy, but they can actually sample over the ocean where there aren't measurements very often. So they give us a view of the whole globe, and God willing, your hardware stays up there for 10 or 15 years as long as you don't run out of cryogen, and you can get a nice long data set. But how do you validate a satellite in orbit? Well, you calibrate it before you launch it, of course. But then you want to validate it. Things are going to degrade in space. It happens to the best of satellites. And so what you need is a network of stations on the ground. In this case, you'll see me use the acronym TCON, which is a set of on the order of a dozen stations worldwide. The dots don't show terribly well, and for that I apologize, but those red dots are operational sites where NASA and Caltech have partnered with agencies and researchers worldwide to set up up-looking infrared spectrometers, near-infrared spectrometers that can be used to validate down-looking satellites. So this network is out there, and it actually measures a wide variety of species because it's a full-on Fourier transform spectrometer, so it's got tons and tons of wavelengths to look at. And there's a lot of information out there, and I'd be happy to talk more about this network if you're interested. But at Ames, we have the blessing and the curse of managing one of these stations down at NASA Dryden, but I'm supposed to learn to call it NASA Armstrong now. So you will have to convert that as well. I will get that wrong several times. It's a dusty, windy place, which I should have realized. So there's a fair bit of maintenance involved with operating that system, but it's a great piece of validation hardware for the satellite community. But how do you calibrate one of those? So if you're going to use that to calibrate your satellite, you have to first calibrate that to, say, the WMO, the international standards. And so to do that, you take an aircraft. Gee, you didn't see that coming, did you? You take an aircraft with a calibrated instrument and you fly a vertical profile over the ground-based satellite simulator. And so that's a mission that we've been doing with our AJAX project. We've got 4 now, and I will hopefully show you data on the next page. That big shiny spot in the middle here is a dry lake bed down at Edwards Air Force Base. Edwards and NASA Armstrong are co-located. They share real estate and fences and security guards and flight lines. So we actually have quite a challenge to coordinate our aircraft into a military airspace. But now that we've all made friends, it's actually really convenient. It's quite close in terms of aircraft travel. So we get a nice vertical profile there. And we're actually optimistic that, you probably can't see it here, but here's Pasadena. No, here's Pasadena. There's a similar system in Pasadena right in the middle of the LA soup. And so we're hoping that we'll be able to share data with those folks and compare the urban site with the hopefully less dirty site out in the Mojave and compare the two after we get some data under our belt. But let me show you the aircraft data, actually, because that's what today's talk is all about. So there are 2 vertical profiles shown here on the screen. Black is September and red is November. We actually have 4 now, but these 2 make a nice explanation. On the top panel, you see the CO2 as a function of altitude for both of those days. And on the bottom, you can see the methane measurements that we made. They're very different. There are some things that are similar, right? Above about 4 kilometers, you can see that there's not a tremendous amount of change in either profile, at least in the CO2. But below, you get some features, and the 2 days are quite different. On the 4th of November, we actually had levels over 400 parts per million of CO2, which is the latest threshold we've crossed in our inexorable climb of CO2 concentrations. This is just a local measurement. The numbers we usually hear in the news are actually a global average. But these are local numbers, and they are higher than they've been in the past. In methane, you can see the same sorts of features that day, a layer up above and a layer down below. And so this is the sort of data that we're using. So we can take the aircraft, and we can help calibrate this ground-based station that will then be used to validate satellites. But like I said, there's only about a dozen of these stations across the globe. So what about everywhere else? How do we support satellites, which is really what our program is designed to do? How do we support satellites in other locations? And now we get to the good pictures. Well, we just take our aircraft to other places. And we put our aircraft underneath satellites. So how does that all work out in the end? Well, I mentioned earlier that there's a satellite that's been put up by the Japanese Aerospace Exploration Agency, and that's called GOSAT. It's the hang on just a second. Gases observing satellite, and they report a column average dry mole fraction of CO2. So what that answer really is if you looked straight down from the sun to the surface of the Earth, took out all the water molecules, but took all the other molecules that were there, counted them all up, put that on the denominator, counted up all the CO2 molecules between the surface and the sun, and put that in the numerator, that would be your answer. And so it's something like these numbers that you've heard. Let's call it 350 or 380 or 400 parts per million. So 1 in 10 to the 6 of all those molecules below the satellite is CO2. But really the only answer you get is that, the column averaged mole fraction. It doesn't tell you anything about where in the column the CO2 is. Is it down near the surface or is it up near the top? Well, I told you that CO2 is a long-lived greenhouse gas. And so you would imagine that it would be mixed pretty well at the older parts of the atmosphere, the higher altitudes where the gas has been removed from the surface of the Earth for longer. And so you can make an average estimate. You can look at measurements over time and you can say, well, in springtime, over a certain place, usually the vertical distribution of CO2 looks like this or looks like that. And down near the surface where we have humans and all of their activities, along with the biosphere and all of its sinks and sources, you can make some adjustments down at the surface based on your best understanding of the carbon cycle. So I'm hoping these green symbols came out. I should have made those darker. My apologies. But you can see blue aircraft data in the squiggly line here. And so it's CO2 in parts per million on the x-axis. The y-axis is in pressure, not altitude, but I'm going to treat it like altitude. So you can see that we measured on this flight up to about 350 hectopascals. So about 350 out of 1,000 of the atmosphere. So we got pretty high. And if you average those into slices, you would get these sort of teal dots. And we do that because the satellite doesn't have infinite information. They handle their data in averaged slices as well. And so you can see in this sort of brown color, these X's give you the first guess, the starting guess that the satellite retrieval algorithm uses to analyze the signal that it obtains. And so they presume that in summertime, in this place, the vertical profile of CO2 should look something like this. And then they adjust it until it matches the answer that they see from orbit. And when they adjust it, they wind up with this bright green answer. Now, I'm not going to say anything subjective here. I'm just going to tell you that they take this vertical profile as a starting guess, end up at this vertical profile as an answer, and we observed this when we were actually there. Now, we didn't go all the way to the top of the atmosphere, and so we need to take some presumptions up above. And so what we've done here is actually take their presumptions from up above the aircraft and just sort of added those on to our data. And then we can calculate a column average mole fraction. And we get this dashed vertical line here on the left. And the answer that comes out of the algorithm for the satellite retrieval is this one on the right. So you can see that actually having in-situ data in the place, in the right time, with some vertical resolution gives you a different answer and tells you more about the atmosphere than if you only had the satellite. So we've been doing this for over 2 years now at this shiny, flat place called Railroad Valley. It's a calibration site for the GOSAT satellite. And we will be doing the same for them and for the new NASA Orbiting Carbon Observatory, which, knock on wood, will launch safely on July 1st, and we'll get to orbit, and we'll be returning beautiful data very, very soon. It's a long road. We're really excited to be a part of the OCO team, and let me show you just a little bit of our data that we've collected over the playa. So here's what our vertical profiles look like from above. They're really just circles. We come up to the site, and by we, I mean our fantastic pilots. I wish I were there, but I've not been. They come up to the site at about 27,000 feet, 25,000 feet in winter, for reasons that we can discuss if you care. Come to the site at about 27,000 feet, and then they make a, I forget if it's a right hand or a left hand corkscrew down from altitude to near the surface. And how near they go depends on conditions and depends on if there are people there, but it's pretty dang low. Then we take that data and we can look at it. We can visualize it in a variety of ways, right? We can plot it here on Google Earth, and you can see that on this day there was a layer in the atmosphere that had less CO2. I've plotted it in blue. I've plotted it in blue for you. A layer that had less CO2 than other altitudes did in that profile. And you go out and you do that 37 times, and you start to see things that are similar and things that are different, and days that are strange and days that are average. And so we're really excited to be able to provide that to the satellite community. Here's a more quantitative way to look at our data. On the top left is methane, and the top right is CO2. And these axes are all in mixing ratio, so it's parts per million for CO2, and also parts per million for methane. This one ranges from about 1.94 on the left, 1.84 on the left to 1.90 on the right, in case your eyes are as bad as mine. Ozone has a slightly different shape, doesn't it, that day? There's a little bit of something up above that maybe is correlated here. So we've been having a lot of fun actually digging into how these 4 different gases do and don't correlate on different days. But this is why you're here, right? I want to show you what it looks like from the ground and from the air when our fantastic pilots go out to take data for us. So let me see if I can find the video. Sorry, I was going to change that to something more professional. I didn't get around to it. Can I make this full screen? Huh. Yeah, right now I'm trying to figure out why the video is so crummy. I'm not so worried about the size of the display.
Nice. Oh, sweet. Nice. Nice. That's the new plane, right? It looked different than the other ones.
So our instruments are on the starboard inboard wing location. So if you get it shot when they leave the playa, you might be able to see that. You see it's asymmetric. The outboard stations are fuel, and then inboard on the right side is our sensor pod. In that pod, we have an ozone sensor at the front. Here, I'll run it again for you. We have an ozone sensor at the front. On the very tip, actually, is the wind sensor. It has 5 holes, including one straight on, to measure the differential winds. And under that is mounted the ozone sensor. And in the middle of that wing pod is our greenhouse gas sensor with pumps and electrical at the back. It's a payload of about 250 pounds, and it's really quite reliable. We've really got the system down with forklift and 4 strong undergrads. We're good to go. Before nearly every flight. If we have 2 flights in a row, we'll calibrate before and then wait till the end and calibrate sort of before and after a campaign. But it's really amazingly convenient to be located just 1 short forklift ride away from the lab, between the lab and the hangar. June is a tough month for us because it's a really intense campaign. JPL and JAXA stage a ground campaign, which is who's filming this and the folks you're seeing. They go out and they measure with spectrometers. They measure the reflectivity of the playa. They walk patterns. It's actually a brutal job. It's 2 or 3 or 4 or 5 hours in the sun. At high sun, they go on the solstice to get high sun. And they walk and to get the distance measurements. And then we zoom in an air-conditioned cockpit and wave and come on home. But since we're paused for just a moment, I will also show you, this one's a really jumpy footage, so see if I can get it to play. This is from the tail-mounted video. So this is mounted up on the tail of the aircraft, and I think you'll be able to hear a couple spots. You'll hear the pilots. So they've already flown for 46 minutes to get from NASA Ames to Railroad Valley, and they're approaching. You can tell that they're actually in their spiral. This is actually the last just little bit of the spiral. It's actually pretty boring to watch the video. It's 46 minutes of getting from here to there. But I figured you'd like this bottom. So you can see the angle they're taking. We've actually learned a lot about how our sensors can handle G's in different directions. And we've gotten the pilots to settle down a little bit, be a little more gentle on our instruments. So sometimes we ask them to do crazy things, and they almost always say yes. But the sensors don't always like crazy things. So the end of this is worth it, I promise. So it was a beautiful day. I presume this was in June, but I can't swear to it. A couple years back. And now they're going to level out and take the last pass across the ply and finish off the vertical profile.
The other one looks like an SD.
Maybe. So it's really a big expanse of boring nothingness, which I think makes it an analog site in some regard or another. And there are some microbes in one of the thermal springs on the edge of the basin, for those of you who care about extremophiles and analog life forms. When we went out in, was it 2012? I think we took along some friends who could do biology, and they investigated a bunch of different sources for biogenic methane, in addition to some local oil and gas extraction sites. Oh, come on, video.
Do those random pixels have any information in them?
It's coded messages from Area 51. I've learned a lot about flight planning, actually. I never thought I would grow up to be a chemist who reads aeronautical charts, but I know where you can't fly, because they're really good sampling sites. Invariably, the place you want to go to get data is right inside or right below or right above something you're not allowed to be in. So I've learned a lot about reading charts. And the Vandenberg, oh, here, I'll let you watch. So this must be a real trip to do this in person. So the Vandenberg exclusion zone is actually right offshore from a dairy in San Luis Obispo that was on a study.
Like
I haven't sorted that one out yet. I'm not sure how we're going to get around that problem. But, oh, you took me back to the beginning. How sad. Well, you've seen all this. So, yeah, we'll go right here. Okay. We'll go here. So in addition to greenhouse gases like CO2 and methane, I told you we also have an ozone sensor on board. And that is actually a really interesting thing when you want to be looking for health effects or the influence of trans-Pacific transport on places like the Central Valley of California, where the air quality is already pretty marginal. And if you get a bad event delivered to you, you really have no hope of having air that meets your standards if you're being given air that's dirtier than your standards, and then you're adding your own local emissions to that. So we designed this flight profile where there's a vertical profile of ozone measured offshore and one measured at Merced. And we've done that for about a year, I think it was 13 months, where we have data that's distributed almost randomly in good flying weather. So moderately crummy to really nice weather. And throughout the ozone season, if you will let me speak of it that way. So in the summertime, local photochemical production of ozone with the extra sunshine is increased. And in springtime, sort of in the March, April, May, even into June, we've found. In that time of year, we actually get delivery of ozone down from the stratosphere to the lower atmosphere. And I'd like to show you a nice little picture plot, data plot of that. First, let me just give you this is another view from the pilot seat. So here's our sensor suite. This is the inboard pod that carries our 3 sensors. This outboard one is a fuel tank, and here's a lovely view of the Central Valley. Here's a plot of the data sort of on a map scale for you. You can see that the higher values, like the greens and the yellows, are down near the surface, and lower values of ozone in the darker colors are up above. But this stratospheric intrusion is really cool. We've actually seen several of these, but I want to tell you about this one because it's a really neat example of how we can apply our data to what you might call everyday life. So if you lived in Wyoming on June 6th in 2012, you would have been exposed to pretty crummy air quality. The air quality in Wyoming, in Thunder Basin, that day exceeded the standards that air for Americans is supposed to be. Well, if you work for the air quality department in Wyoming, you need to find out if that was local pollution that you need to mitigate so it doesn't happen again, or if that pollution was delivered to you and there was really nothing you can do about it. And if it was delivered to you by what they call an exceptional event, some of those have been big, big wildfires, and some of those are stratospheric intrusions. If air is delivered to you by an exceptional event, you can petition to the EPA to have it removed from your permanent record. You can ask them to erase that black mark against you so it doesn't count against your tallies. And if you have too many of these exceedance days, you have to develop a state implementation plan on how you're going to clean up your act, and it's a lot of regulation that comes to your area. So when there is truly one of these cases that's out of your control, states try to petition them to the EPA and get relief. By complete coincidence, in fact, I think it was entirely by coincidence, we had flown the day before. I don't have a crystal ball, but we have a good meteorologist. Oh, he went and got a job. Our intern got a job. Matt was a great forecaster, and Matt and Emma were working together to look for stratospheric intrusions, and this one we had sampled the day before. We hadn't met the folks from Wyoming yet, and you never know where these are going to travel. But if you can see this faint black line going across the coast of California, that's actually that flight track I've shown you before, vertical profile offshore and one onshore. The color map that you see underneath is a model called RACMS, a model that produced ozone in its forecast. And high ozone is red and low ozone is blues and greens. And so you can see what the model would have predicted that we should have seen. And the agreement is pretty good. Our data has a lot more fine scale features. The model's pretty coarse. It's a grid model. But if you take this map and you slice it along 122 here, 122 west, and you lay it out in the bottom like this. So now we actually have an altitude axis on this bottom plot going from 0 to 14 kilometers. And 30 degrees north up to, I don't know, let's call it 50. From left to right, all of it along this 122 west longitude line. Red is high ozone again, blue is low ozone. And here's where you can see our vertical profiles. So they start at the top and they come down to the bottom. There's actually 2 of them in there. And what you see is that we observed, what the model predicted is what we observed, which is lower ozone in this sort of middle altitude, higher ozone sliced right in between, and lower ozone down near the surface. And this tongue is actually drawing down ozone that was formed naturally up in, well, that we presume was formed naturally up in the stratosphere. It might also have been ozone that was delivered from very, very far away at high altitudes. But it was drawn down from very high altitudes, and then, if you follow the model 24 hours farther, delivered it to Wyoming. So by happenstance, we had this data that helped Wyoming to prove their, well, to make their case. It's still being, I don't know, ruled on. And so our data has sort of gone into their packet along with all of these modeling studies and all of their ground-based observations to try to put some reality to the observations and to the rulings on the ground there. So we're really excited about that. Not only does our data help the modelers to improve their forecasts because we have much finer resolution, and the topography is real in the real world, and in the model the ground level is not always getting over into the Central Valley and then back up again. The ground level is not always at ground level, which has been interesting to learn. So we've been really excited about these stratospheric intrusions. We've captured a handful of them, and the season's coming. So we'll be looking for them again soon. We have a paper that's just come out in atmospheric chemistry and physics, and I will happily pass along that URL or copies of that if you'd be interested. And I know you're here for the photos, So forest fires are awful and they're horrible when they hurt people or the ecosystem. Sometimes fire is a good thing in the natural ecosystem, and sometimes fire is a good thing when you have a friend at San Jose State who measures the micrometeorology of fires and has a truck outfitted with all kinds of gear and is just geeky enough that he checks his email at all hours of the day. Because then when you find out that your aircraft is ready to go and his truck is ready to go and you've got undergrads and grad students at your disposal, you can send them out to Yosemite to make some really cool measurements. So here's some pictures that were taken by Matt, our meteorology intern, and the San Jose State team when they went out to look at the wind structure and the particle loading of a particular place. You know, they went to the edge of the safe zone and stopped and looked out across the plume. So this was maybe a week into the fire, if I'm remembering correctly, and the smoke was just ridiculous. I mean, absolutely, it looked like it was dusk from the way Matt described it. This is the truck that Professor Clements at San Jose State has outfitted. The wind lidar is up here. That's this part of the gear. And I think that's the Met station there. Hard-working students. They launched radiosondes to get wind and temperature and pressure and relative humidity profiles and to watch how the balloon traveled with the wind. And then we sent our payload with our very, very obliging pilots to go have a look. And so you can see, here's the line, here's the front, basically, of the fire. And they're coming up from clear air, coming up at a distance. And they will get closer. And a little bit closer. And so we've got all sorts of neat granularity in our data. And so you can see some of that. So all right. Here, back across that east, you can image forth, and if you can see it here, there's 1, 2, 3 altitude levels, and the data at the top is boring and clean, in dark blue here in methane. And that bottom level, though, you can see some higher amounts of methane. You can actually see it underneath in the CO2 also. So we've got some really nifty data in across the plume. From this one happens to be the 29th of August. And then we can plot it up and do all sorts of great analyses on this data. And I'm going to look and see how much of this you can actually see. Okay, not a lot. I'm going to skip right ahead and put my big circles on there. Presuming that your eyes are as bad as mine, I've given you guides. Look here in the red circle. What I have plotted is ozone enhancement, so delta ozone, relative to background, on the y-axis of the left plot. On the x-axis of the left plot is the enhancement of CO2, again, relative to a background amount. You can see that most of the data from the flight bundles down in this bottom left corner, except the stuff that is conveniently plotted in red, which if you check the time log on the flight is the stuff that was in the plume. It sits very differently on this plot of ozone enhancement and CO2 enhancement, very differently from all the rest of the flight. Similarly, if you look at enhancement of methane on the vertical axis of the right-hand plot, and again, enhancement of CO2 on the x-axis, again, you get this red blob of points that just jumps right out as being very different chemically from all the other air we sampled that day. The tiny little legend over here is telling you that the red was identified as fire plume times. The purple was identified as a time in the flight when they were sampling haze in the valley. And the green was a time period of the flight when they were taking a vertical profile in the San Joaquin Valley. Very, very different. It has a completely different slope on that plot. It's a completely different air mass. And so this method of looking at the chemical composition of chunks of time on the flight can tell us a lot about different parts of the air that we traveled through. So on September 10th, we had another opportunity to go fly around the fire. Things had really calmed down a lot. I think it was 75 or 80% contained by the Forest Service, by CAL FIRE standards. The combustion was a lot less vigorous. They did a similar sort of thing. They went across the plume. They transected the plume at a variety of altitudes. Here's data. I'm plow through. We're getting a little short on time. But you can see, again, there's this red set of data. Oh, sorry, that's the plot from before. For comparison, here's the new plot, you know, about, what, 12 days later. You can see that the red data is still under there. There's several different colors now. Several different chunks of time have been sorted out. So red is still fire plume, and I've made the slope much more readable for you up here. Look, it's changed. That's what you're supposed to notice here. 2 weeks later, this ratio of methane to CO2 has gotten a lot larger. And that's to be expected from smoldering combustion, actually. It's less complete combustion and more methane relative to CO2 is being emitted by the fire. So we were really pleased to be able to see that. This is one of the first times, as far as we can tell, that a wildfire has been sampled, a forest wildfire. Most of the measurements in the literature are either done in a lab setting, I'd like to see that lab, or a prescribed burn. So you know they're going to burn Henry Coe State Park, and because they have to put in the permits and you have to wait for good weather, and so you run out to Henry Coe State Park and you sample. And that's true data, but it's under a good weather condition with a known fuel loading. This was a wildfire in Yosemite. And so we're really excited to see that these ratios do what they've been predicted to do. And there are times when we get surprises, like this one here. The San Francisco Bay Area portion of the flight in the light blue has a quite similar slope to this original early plume fire. And you might think, wow, I wonder what that is, until you actually remember that this was the day that the Mount Diablo fire caught. So as we were taking off from Ames, which I swear I didn't realize this until about 18 hours later. So we were taking off from Ames. In the distance, you could see the Mount Diablo fire. So we think they crossed that plume as well. And so these chemical ratios really give us a good handle on understanding early fires, late fires, and what we're actually sampling during a flight. We started looking at Sacramento. This is 2 days, the 12th of April across the top, and the 29th of October across the bottom. I've got methane first, then CO2, and then the ratio of methane to CO2. And you can see that it's anything but uniform across an urban area. And that's what you'd expect. We have a landfill here, and we have a power plant there, and people live here, and cows live there. And there's a lot that needs to be learned about how humans in urban areas impact our atmosphere. I'm going to speed up a little bit because somehow I actually didn't speak fast enough. We have a set of data from about a year ago now when there was a NASA aircraft campaign in the area. It was called Discover AQ, and there was a DC-8, P-3, a big aircraft full of all kinds of instruments you could imagine. And they mostly stayed down near Bakersfield. Well, who cares about Bakersfield? We care about up here. So we went out flying on the same day, but further to the north. And they were here for a couple of weeks, and we flew a bunch of different flights. And then we found ourselves a modeler who can run a chemical model. And he took our data, and he decided that our data, such as the data I've shown you here, although this happens to be a plot of ozone. So here's Merced, here's Madeira, this is Los Banos, for those of you who might know the area and want to be orienting yourself geographically. Here's Ames. If you take all of our greenhouse gas data and you compare it to what a model would predict for this area at this time, you find out the methane is crazy wrong. Crazy wrong, my adjective. Our colleague Matt was much more political and much more quantitative in his study. My answer is crazy wrong. So people are starting to find this. It's about the third time now I've heard reported that observations in the atmosphere show much more methane than all the databases and reporting inventories suggest that there should be. So clearly something's up, and it looks like it's livestock. In some places, it's oil and gas, leaking pipelines, leaks that aren't reported, leaks that aren't known. But around here, it looks like livestock. And so if you adjust the emissions in the model by a factor of, I think it was 7, you can get the right answer, which means in some places in California, it looks like, at some times, methane from livestock is underestimated by a factor of 7. Methane's a killer greenhouse gas. It's 20 times stronger than CO2, and it's going to rise in its quantities in the atmosphere. So this is sort of a new hot topic for us. I'm trying to come up with a good cow manure joke. I mean, there's a lot of them out there. I think I'm going to skip that one because I want to make sure that I leave a little time for cow poop jokes and questions. But first I have to tell you that this is an incredible team effort. I may be the pretty face, but there are a ton of people working on this project and have been for years. And so this list I'm sure is incomplete because I wrote it. And whenever you write one of these lists, you invariably forget someone. And the picture is incomplete because our team is never in the same place at the same time. But I need to thank Emma and Tamaki, our postdocs, who are carrying the load of all of the data analysis and instrument calibration and maintenance. Warren Gore, who is the lead and constant calming presence in our team. I'm the highly caffeinated one, and you can see our pilots there in flight suits in that photo. Ken and Rob and Don and John in the early days. This project would be nowhere without them and without the generosity of their company. And we can do all sorts of really amazing science because they're willing to give it a try. And they will say uncle once or twice, but that's about it. Only once or twice if they ever told me I'm crazy. And one of them was, can you do the LA basin? And they looked at me. And they tried to decide if I was kidding. And then they laughed, because the LA basin is a place I would love to go, but you cannot get into that airspace. Everything else, though, they have been incredibly amenable. And tons of colleagues up and down. We like to make fun of to our project. This picture, but there's pretty many questions that Adrian will look at.
So Laura, I don't know, maybe it was back about slide 20 or so, you were showing methane and CO2 measurements as a function of height, and it appeared that they were anti-correlated to some extent. Is it possible that there might be some displacement of CO2? I don't know what mechanisms might.
So I'm presuming you were thinking of this graph, which is more easily read than some of the others I showed you. So let me see if I've guessed the right plot.
Yeah, that's the one.
We've seen both phenomena, correlated and anti-correlated, for CO2 and methane. This is Railroad Valley, so this is pretty far away from sources and sinks. There is a little bit of local petrochemical, but it's really small scale. And these altitudes are too high to have been influenced by the very local sources. So this is likely to indicate the history of the air mass. So that CO2 is drawn down, which could suggest that that air used to be near the ground, where a biosphere could have removed some CO2 from that air. This was a summertime flight, so if that had been over an area that was actively growing, it would have drawn down the CO2, and then if that air maybe picked up a little bit of local pollution, could have picked up some methane.
Okay, so it's unusual to see them anti-correlated.
I wouldn't say unusual, but it is more common that it seems to depend on the time of year, actually.
And this is, an OCO is going to get us both of these measurements. In fact,
unfortunately, OCO2 will only have the CO2 measurement, but GOSAT does have both.
Okay. Yep. So maps are coming of the correlation.
Column average.
Right.
So the layering like this, and it's an open question, can these layers actually be observed with just a column average? And that's something we're trying to figure out.
Hi. Is there a way that they could capture this methane for so it doesn't go in the atmosphere and they can use it for producing energy?
That is a great question because it gets me right into my poop jokes. So I have a 3-year-old and I'm finally just out of the dirty diapers, so I need some new poop joke outlet. So thank you. Dairies actually are a big source of methane. So some farms and some industries do recapture. And landfills, right, a covered landfill, the newer designs have a methane capture system already. Sometimes you'll see them flaring them on the sort of a medium old design. But yeah, methane, it's a great fuel. It's got a price, right? I mean, you should be able to make some money off that. There's a reason to try to capture it. And so there are instances of farms, dairy farms, I think in particular, that have already shown that this can be done. If you design your manure pond with a gas capture system, you can very easily capture burnable gas and use it to run your farm. In fact, you can become almost, depending on the size of your operation, an energy neutral farm using your own manure gas. So yeah, actually, there's some talk about if the livestock in California is as wrong in the inventories as it is like it might be, and if you look at how the cattle are distributed, most of the head cattle that are managed in a way that produces the most methane are owned by a small number of companies, actually. So if you could hit, say, the top 10 companies and convince them to convert to a system that captures, you would be capturing like 80% of, it wouldn't be the market, but you could do it with a relatively small number of companies, from what I understand. Not a political statement.
Hello, back here.
Thank you.
Sure. I don't want to have you staring into space at the SETI Institute. They think you're looking for little green men. I have a question about that last statistic about the modelers being 7 times off. Not quite in order of magnitude, but still pretty disturbing. And so it's a two-part question. One is, what's wrong with the models? And are they using your data to improve their models in some way? And does this imply that the climate models for everywhere outside of California are equally off, possibly?
So in trying to cram a lot of information into 55 minutes, I oversimplified. So let me fix that a little bit. There's two things going on. One is the model that moves emissions around with winds and has chemistry in it to let the molecules evolve with time as they're exposed to sunlight. But the model is fed from underneath by an emissions inventory. So that emissions inventory, you can choose this one or you can choose that one. You can choose the one from the EPA. You can choose the one called Edgar. You can choose the one called Gaia if you're using Biosphere. And so people have been putting literally decades of effort into building a variety of these different databases. If you want to see what humans are doing in cities, you would use Vulkan or Hestia, depending on if you want to go block by block. So there's a bunch of different emissions inventories out there. And really what seems to be wrong is the one particular emissions inventory. And part of the problem is that inventories take a long time to accumulate, and they're often voluntary. And time marches on. So even if it was 101% true 5 years ago, it's no longer true. And just the data gathering delay time. So that's part of the reason atmospheric measurements are so important, to make sure we're anticipating growth properly. Now this other part that we've seen is that certain specific industries is the wrong word, sectors. Wetlands sector, fossil fuels is a sector, livestock and agriculture is a sector. Certain sectors are better than others. Right? You know how much gasoline is pumped at the pump. You pay taxes on it, right? That's pretty well known in this country. Same with natural gas that's sold. But natural gas that leaks, you kind of have to go with what the industry says they took as a loss. They may not want that known. They may not know what they're losing if it's an unmonitored site. So there's lots of reasons that different sectors could be right in some places and wrong in others. And there's been some work in Salt Lake City that came up with a number, and I'm trying to remember, so it's probably wrong, but it's of the order of a factor of 2 or 3 for the natural gas and oil in, it was either Salt Lake City or the state of Utah, I forget. So depending on where you are and what your industry is and how fastidious they are about their maintenance, those inventories are going to be a little wrong here and a little wrong there, and spot on here for a day before we have more industry and more people. So there are lots of problems with any model. There are lots of problems with any inventory, and my data are perfect, of course. So since I have perfect data, I am very eager to share it with any modeler who wants it, get it in there and show them what they can learn about their model, about their emissions inventory, with our very small geographic and temporal information. It fits an oval, so it's got to be perfect.
Laura, I'm over here. Thanks for a great talk. Since this is an astrobiology organization, I feel I should mention what you know well. The methane is not really coming from cows, it's coming from microbes.
Exactly.
Everywhere. And that's why when what now seems to have been incorrect sensing of methane on Mars was not interpreted as there being cows on Mars, but microbes.
Very correct. It's the microbes in the intestinal system, in the digestive system, microbes in the waste ponds, and we did find a little bit of microbes in the warm springs in Railroad Valley.
And swamps and all sorts of places.
And my son's diapers. Just one more diaper joke, just to get it.
So who's producing all the CO2 and methane actually, for the most part? I mean, and how is this distributed geographically? Then the second question is, could your aircraft data be supplemented with balloon data, for example, which might give you a longer timeline to work with?
Second question first. Balloon data. There's actually a really neat sampling device that's been recently developed by some folks at NOAA that we're hoping to work with, and they launch it on balloons. Balloons are great because if your payload is small enough, light enough, you can fly in a lot of places. If you're less than, I think it's 8 pounds, you don't have to worry too much about what airspace you're in. So balloons are a great opportunity to sample a lot of geography, but still really only over land. Because a lot of these lightweight payloads, you have to go retrieve and collect the air and then analyze it after it's come back to Earth. So you want to be sort of within a few hours drive of it when it lands. But balloons are a great way. In-situ data will always be sparse in geography because there's only so many of us and only so many flights and so much time that you can do. So satellite data really does give us the global coverage that we would need to study the bigger picture. And so you asked about emissions of CO2 and methane.
Right. Who and what is doing it mostly, and how is that geographically distributed?
So there's lots of ways to slice that question. We could answer it per capita. We could answer it country by country. We could answer it industry by industry.
Over the area that we're covering here.
Right. Well, because it's transported globally, you really can't leave anybody out, right? So, so here in the Central Valley, say for the lowest levels of the atmosphere where we think the air that we're sampling has been influenced locally, we're looking at things like livestock and agriculture, as well as in the southern Central Valley, down near Bakersfield and a place aptly called Oildale, looking at emissions from petroleum, from fossil fuels, from natural gas, in the lowest levels because they would reflect the local area. At the higher levels, it does reflect air that's traveled. I mean, you've watched the weather maps, right? Air weather systems come across in a few days from outside our line of sight in the middle of the Pacific across the U.S. in, say, a week. So that air is coming from other places.
And how about rural versus cities?
Since a large fraction of the CO2 and methane that we're talking about here is related to human activities, I would say it's actually linked to sort of where the money is in a way. Like so people live in the city and their fossil fuels are emitted in the city, but goods can be manufactured outside a city, or a farm or a dairy would be outside the city. So you really have to look at the energy intensity, which in a way can be aliased onto money.
I have just one more question from me. Why is ozone going to track a bad day? Can you tell us a little bit more about what's happening when the ozone production, for example, for your days in Wyoming? Why? I mean, this is obvious to an atmospheric scientist, I know, but why does an ozone high reading equal bad air?
Well, that's the component of bad air that we care about. It burns your lungs, it makes your eyes sting, it damages living tissue.
Right.
And it is produced in photochemical smog.
So
it's one of the products of pollution sitting in sunlight.
So where are those the bad ozone going to come from off the coast of the US? Where is that coming from?
So continents that are upwind, so say in Asia, if there is pollution that is emitted and then lifted to an altitude high enough to catch the winds, and that's brought across the ocean and down again, all the time that, let's say, gasoline that's spilled on the ground or nitrogen oxides that came out of a combustion engine, all the time that air is traveling, it's actually up at a cold altitude. It's kind of dormant. And then when it gets delivered by a weather pattern, gets delivered down to a warmer altitude, say here in California or up in Oregon, then the chemistry turns on again when it gets warm. And so those pollutants will then be degraded to form ozone, perhaps formed locally from precursors that were emitted far away.
I'm just going to get one more question.
Thank you. Any plans to fly over Black Rock City, Burning Man, just before and during?
So cool.
Because you could have ground-based stations measure
That
and
would
look
be really
60,000 people or so.
And
You
I
have
know the guy
call
who would
map-
do the. I know the guy who would do the ground
Who would
station
volunteer
too.
for this?
Oh yeah, I know who I would call.
And then you could do a column average altitude profiling.
Is there burning in daytime? Because the satellites generally need visible light. Because, okay,
Sure, there are
somebody in this
60
room knows, right? Most of the burning's at night, or is some of it during the day at Burning Man?
No, burning is at the end of the question.
But is it all at night?
It's at night. It's at night.
Have to find out about thermal channels.
Mostly the last night. But you have, they set stuff on fire all through the night. But you have 50,000 people collecting at a place.
Mm-hmm.
There's nothing else, no vegetation, so you can
Very cool. Very cool. I presume it's not restricted airspace if people are out on the ground. So I think I have a new project. Thank you, Kadar. That sounds like fun.
So, Laura, we have a special setting mug to go with your new project. I'm sure you'll
Oh,
be
wow.
writing about it
That's really
and needing
cool.
a lot of caffeine stimulation at that time. Continuing caffeine stimulation.
Thank you.
Please join me in thanking Laura for a great talk. And